Okay, if we think about this first question a little bit, what if we have this equation and we want to find some y function that satisfies it? Remember, we can find any old y function that's going to constitute what we call a particular solution. Well, all we have on the left is a combination of derivatives of our y function. So what sort of functions have derivatives that could give us something like t squared? The obvious answer is powers of t. So y should be a combination of powers of t. In other words, a polynomial. And these powers should be integer powers because we're getting an integer exponent on our derivatives. Now, we'll observe that successive derivatives of powers of t have decreasing powers. If we start with t to the fourth, our derivative is going to be a multiple of t cubed. The derivative of that's going to be a multiple of t squared, etc., etc. So, from this we can see that y of t had better not have powers higher than 2. If it had powers higher than 2, then the higher derivatives, if y had powers greater than 2, the higher derivatives would have powers lower than that, which would leave us some power greater than 2 in our y function. And our total sum from the left-hand side has to have a power of just 2. So if we had what we might call an unprotected power of 3, let's say, in our function y, none of the higher derivatives would be able to get rid of that power. We'd be stuck with that power and we wouldn't end up with t squared. We can also think ahead to say that powers less than 2 when you take their derivatives could combine to cancel, I don't like that word, but cancel lower powers. And leave t squared. So this gives us a trial function of the form at squared plus bt plus c. This would be our y function. Our derivative would be very clearly 2at plus b, our second derivative 2a. If we put these functions together in this equation, we're going to have little a times 2 times big A, little b times this, and little c times this. When we add them all up, we're going to end up with a power of t squared, a multiple of t squared, a multiple of t from here, here, and constants from here, here, and here. If we do this and plug it into our equation, whatever the equation might happen to be, we'll have to get left-hand side has got to equal the right-hand side, so we have to get t squared, meaning that the coefficient of t squared has to be 1. And we're not going to get a t, and we're not going to get a constant term on the right-hand side, so that the coefficient of t is going to have to be 0, and the constant term is going to have to be 0. When we do this, just plugging these three equations into this equation, we're going to get, plugging the y function and its first and second derivatives into this equation. These conditions are going to give us three equations in A, B, and C. They're actually going to be linear equations, and we're going to be able to get a solution. Now, what if our equation was ay double prime plus by plus c, by prime plus cy equals cosine of t? How do we get a function that solves this equation? What function would we take derivatives of to get a cosine? Well, we could take derivatives of cosine functions, and we can take derivatives of sine functions. A second derivative of a cosine function, which we would get from the ay double prime, can give us a multiple of the cosine. A first derivative, which we'd get from y prime, could give us the first derivative of a sine function. If we have the sine function in our trial solution, our first derivative term will give us a multiple of the cosine. Of course, if we have a cosine in our trial function, our first derivative is going to give us a sine, and we're going to have to get sines in these other terms in order to take care of that, but that works out fairly easily. A trial solution y equals a cosine of t plus b sine of t is going to give us y prime equals negative a sine of t plus b cosine of t. Well, I'm not going to read it to you. You can see what these derivatives are and higher derivatives are going to give us. It should be clear then that if we plug these derivatives back into this left-hand side, we're going to get some combination of cosines and sines with the coefficients little a, little b, little c, and the big A and big B coefficients. So when we plug these solutions into our equation, we're going to get some linear combination of sine t and cosine